In this example, we're going to look at quantized charge. Specifically, we're going to calculate the number of electrons in a block of copper. So I give you a 1 kilogram block of copper, and it's been charged to plus 10 millicoulombs. And I ask you how many electrons are in this block. And I give you a couple pieces of information, the atomic number and atomic weight of copper. And so we can handle this problem in two parts. First, let's calculate the number of electrons in neutral copper. Then, let's calculate the number of electrons that are taken away when we charge it up to plus 10 millicoulombs, and then we can combine those two numbers. So let's start with the first part. First, I'm going to calculate the number of atoms in my block of copper. So I'm going to start with Avogadro's number, 6.02 times 10 to the 23rd atoms per mole, and then I'm going to convert that into atoms per gram using the atomic weight. So 1 mole is 63.5 grams. And then I'm going to convert the weight to kilograms. 1,000 grams is 1 kilogram. And then finally, I'm going to multiply it by the mass of my block, 1 kilogram. So this should look very, very familiar to you from your introductory chemistry courses. And when you plug in the numbers, you should get 9.48 times 10 to the 24th atoms. Remember, if we want to find the number of electrons, we just take the number of atoms and multiply it by 29. There are 29 electrons for every atom. And so I get 2.75 times 10 to the 26th electrons. So now that we've calculated the number of electrons in neutral copper, let's look at the plus 10 millicoulombs. So once again, I'm going to look at the number of electrons. I know 1 electron is 1.6 times 10 to the minus 19 coulombs. That's the elementary charge. I'm going to convert coulombs to millicoulombs. 1 coulomb is 1,000 millicoulombs. And I'm going to multiply it by the total charge that I'm given, 10 millicoulombs. And so when you plug in all the numbers, you get 6.25 times 10 to the 16th electrons. So now let's take a look at these two. In the first part, we calculated 10 to the 26. In the second part, we calculated 10 to the 16. Well, 10 to the 26 is 10 orders of magnitude bigger. It's way, way, way bigger. So we really don't even have to bother with the second part because, given the number of sig figs we're using, that 10 to the 16 is insignificant. Even though it seems like a big number, it's really not in this case. So our answer is 2.75 times 10 to the 26th electrons. So just to go over some final thoughts, you already saw the number of electrons in a metal is enormous. Even just a 1 kilogram chunk, just a couple of pounds, is a huge number of electrons. Second, for large chunks of metal, and large doesn't even mean that big, just a kilogram or even less, we can ignore that extra little bit of charge, 10 millicoulombs or however much you charge it up. But I want you to think about something else. When would that charge of 10 millicoulombs start to make a difference? So try this problem again, only start shrinking the mass of that chunk of copper down. And try and figure out at what point do those 10 to the 16th electrons start to make a difference. And you might be surprised at how small the chunk can get before you really have to take them into account.